Archaeometry is the use of scientific techniques that come from chemistry and physics and biology and also scientific methods such as mass spectrometry and X-ray diffraction to answer anthropological and archaeological questions. So we're going to look at a few techniques, give you some examples of what they are used on, or the kinds of materials they're used on, and what kinds of information they give archaeologists. So one thing archaeometry can do potentially is to authenticate artifacts of unknown provenience, right? So that is, the artifacts maybe came from a collection, but not from an not from a recognized archaeological site, and so maybe the collector doesn't know exactly where that object came from. Archaeometry can sometimes be used to tell whether the artifact is real or a fake. In this case, this was a box that appeared on the antiquities market in the late 90s. It was an ossuary box, secondary burial box from Israel, and typically at the time, around the time of Jesus, during Roman period, Judea, people would be buried in tombs, and when their bodies had decomposed, their bones would be collected into a small limestone box with the name of the individual on it. Now, in this case, this box became very famous because it had an inscription that read, James, son of Joseph, brother of Jesus, Yeshua. Right? So it was in Hebrew. And so the collector, you can see him right here, and the size of the box, claimed that this was the box of the half-brother of Jesus, James, who was important in the early church in Jerusalem right after Jesus' crucifixion. And this made quite a splash all over the biblical archaeology world and the scientific world and the news media. Now, he did not state where it came from. He didn't even state where he got it from. People were very skeptical, including a geoscientist from Israel, I think from Tel Aviv University. And so what he decided to do is to examine the patina on the box. You could faintly see the inscription here. The patina on a limestone box, and you probably have seen the patina on some of your limestone headstones, is formed from water, dissolving minerals, and the water evaporating, leaving this kind of coating of minerals on the outside of the limestone. Now, if this was an authentic artifact, and some people thought that the box was authentic, but the inscription was added later, what he decided to do was to scrape out patina from inside of the inscription and scrape off patina from the box and examine them. Now, if this was authentic and the inscription was carved at the time that the box was made, the patinas should be identical. What he found was that the patina inside the inscription was different from the patina on the outside of the box, meaning that this was an ancient stone ossuary box with no inscription, and the inscription was added later to give it more value. Police raided the collector's home. They found the ossuary box. It was a whole court case. And one of the other objects that this collector also released onto the antiquities market was another Hebrew inscription. This one supposedly talks about renovations that were made to Solomon's temple. And again, scientists thought the same thing was going on here, that this was a ancient stone that was never carved, and then a inscription was carved on it. And again, they looked at the patina inside the inscription versus the patina on the outside of the stone. And in some cases, it looks like some of the leathers actually go over the broken edges, which means that the leathers were added on after the stone was already broken. Right? So potentially, archaeometry can tell whether something is authentic or not, but not always, and it's not always correct. I'm going to give you an example of that. It's a technique, so people can misinterpret things. For example, if you have a marble statue at a museum and you test the marble and you can tell that the marble comes from Greece, that doesn't necessarily mean that the statue is an authentic artifact, because they could have gotten that material from Greece and then forged a statue to look like an ancient statue. Another interesting piece comes from medieval paintings, where sometimes people scrape the outside of medieval paintings, test the paint, and then decide that the painting is a forgery, without realizing that paintings were retouched and repaired over time. And so if you're not testing the original paint from the time that the painting was made, you might actually get an incorrect date. You might be testing paint from a later repair and not the original painting. Now, when we think of repairing artwork, it reminds me of a very infamous case, I should say, in Spain, where in a church there was a painting of Jesus, and one of the women who worked in that church decided that she was going to restore it on her own with no background in art conservation at all. And this was the end result. You can see she turned a 15th century painting or a 16th century painting into a Picasso. And she was actually very annoyed when the church didn't pay her or reimburse her for her restoration work there. But you can see it's kind of funny, but not so much. So archaeometry could potentially tell you whether something is real or a forgery. Okay, another important technique. Now, this is a technique called elemental analysis. We know about, you guys probably have taken chemistry in high school. We talk about compounds like H2O or CO2. Those are elements that are combined to form, a complex structure. Elements are the smallest units of a substance, right? So H2O is comprised of hydrogen and oxygen, obviously. Now, with elemental analysis, what you're doing is you're breaking apart a substance into its different elements. Not its compounds, but its different elements. And this is particularly useful for obsidian sourcing, because different geologic outcrops of obsidian are chemically different from each other. So if you have an obsidian tool, what you could do is look at the different proportions of the elements and then match them up to known sources that you have already sampled. And you can trace obsidian blades or obsidian tools back to where they originally came from. This is something that's been used all over the world. Wherever there's obsidian that was used in ancient times, you can use this technique. Right, so looking at the proportions of different elements, it's a very, very useful technique. Now, using this and similar techniques, archaeologists have been able to trace trade routes all over Mesoamerica. Now, what if you wanted to source clay on a clay pot, and you wanted to see if it was made from local clay or from clay somewhere else? Maybe you wanted to see if that pot was traded from somewhere else or if it was locally made or away. So what you could do is you could examine the minerals inside of the clay of the pot and compare it to the minerals inside of a local clay source or clay sources from different areas to see if they had the same proportion, the same kinds of minerals. Now, the way you would do this is you would take a thin section of the pot, put it on the slide, and use a special microscope that uses polarizing light. Using polarizing light, different minerals like basalt and quartz and mica would show up as different colors. Under ordinary light, they would just be, yellows and browns and white. But under polarizing light, they would show up as blues and purples and pinks. and distinctive colors that would allow you to identify them as one kind of mineral or another. You would look at the proportion of different kinds of minerals and be able to say, yes, the clay in the pot is almost identical to clay from a local source. Okay, now what if you wanted to look at residues? That is, you have a residue inside of an ancient pot. You wanted to figure out what was in that pot. Well, you wouldn't use elemental analysis because you could have the same elements making up different compounds or different substances, right? So, for example, you could have, H2O, and you could also have hydrogen peroxide, and they would have the same elements, hydrogen and oxygen, but just in different proportions, or carbon dioxide, CO2, versus CO, carbon monoxide. If you did elemental analysis, it would tell you had carbon and oxygen, but it wouldn't tell you that you had either carbon monoxide or carbon dioxide. So you would have to use a different technique called mass spectrometry. The way mass spectrometry works is it allows you to look at compounds. A substance is broken up into different compounds through evaporation, and then those different particles are detected and their molecular weight is given to you. Using the molecular weight, you could identify what compound it is, whether it's, let's say, like in this example again, CO2, or whether it's, lactose, or a certain kind of, barley, or a certain kind of tannins from wine. You would be able to identify that compound. Now, this has been used a lot in archaeometry, especially with residues on the inside of vessels. This is a particular vessel from the Maya world that had the name of an important Maya elite on it, and also Maya glyphs that spelled out cacao. And cacao in the Maya language is cocoa or chocolate. And when they actually took the residue out and analyzed it, it turns out it was cacao, it was chocolate. So the name on the vessel gives a clue as to what was actually inside. So archaeologists have used this to identify what is inside of pots, and they have looked and been able to identify, for example, the earliest dates of the use of milk, the earliest beer, the earliest wine. In fact, an archaeologist who's done a lot with ancient alcoholic beverages, this guy Patrick McGovern, he identified the earliest beer and the earliest wine in the Middle East. He worked with the Dogfish Head Brewing Company to recreate some of these ancient brews, including a mixture of beer and wine that was found inside of the tomb, in one of these vessels of King Midas. Yes, there actually was a King Midas. He was buried in a tumulus here, you could see, in modern-day Turkey. So that's mass spectrometry. Okay. I'm sure you've all heard the expression, you are what you eat. Well, it turns out to be true in terms of chemistry. You can take the bones of an ancient human and you can analyze them looking at stable isotopes. Remember, we looked at radioactive isotopes of carbon, like C14. We said there were stable isotopes too, isotopes that don't break down. Carbon-13, and also nitrogen-15 is a stable isotope of nitrogen. Well, it turns out that marine animals and plants and different kinds of terrestrial plants will have different proportions of C13 or C12. And when you eat these different animals and plants, the C12 and the C13 are absorbed in your bones, and they show up in an analysis, in a chemical analysis of your bones. So, for example, you could take an ancient human skeleton and you can determine whether that person ate more C4 plants, such as maize, or more C3 plants, such as beans. Or did they eat a lot of fish? Or did they eat a lot of marine animals? Right? So, typical ancient diets, ones that were heavily reliant on marine mammals and fish, the Inuit and the Haida, or marine plants like and fish, and fewer marine mammals would be Denmark during the Mesolithic. C3 diets like wheat and barley, that would be the European Neolithic, and then Mesoamerica, C4 diets, where you would have a lot of maize. So you could actually look at skeletons from different periods and see how the diets changed over time by looking at stable isotopes. That's something we'll talk about more this week and next week as we start to look at human skeletal analysis. Okay, a couple of more examples. Metals, like you saw with Ulfbert, you could also do other kinds of analysis on not just the amount of slag in the metal, but proportions of different kinds of, how much percentage of tin in the bronze, for example. This is something they did with the Liberty Bell, which you can see here, which is in Philadelphia. The Liberty Bell was cast in England, sent to the colonies, put in the church in Philadelphia, and it cracked. It was recast. It actually cracked again, but they didn't cast it after this. They just repaired it, like you can see here. Now, what scientists did is they tested the metal from different parts of the Liberty Bell. And what they found is that the proportions of the bronze were different in different sections. That is, this was not homogeneous and it was not uniform. Now, what does that mean? It means that different crucibles were used to pour in the bronze. That is, they didn't have a crucible large enough to cast the Liberty Bell, or to recast it in one go, right? That is, it had to be done in stages, pouring in one crucible, then another crucible, right? And those different batches of bronze were slightly different chemically from each other. So we can tell a little bit about the Liberty Bell from scientific analysis. Okay, another analysis, and this is something that's getting more and more refined, and some of you may have participated in this, is ancient genetics, right? Paleogenetics, where they try to match up, let's say, modern DNA with ancient populations, or they try to use ancient DNA to track migrations through time, right? It's very, very complicated, and the science is changing all the time. It's becoming more and more refined, right? I did this, not that long ago, and mainly what my DNA shows is a mostly Mediterranean, southern Mediterranean, and eastern Mediterranean origin for the populations I'm descended from. You could also use this kind of DNA, though, to test other things besides people. A famous example was the Dead Sea Scrolls that you can see here, which were found in the cave in the Dead Sea. There's debate about the Dead Sea Scrolls. Some people believe that they were all written by a small community that lived somewhere in the area. Other people believe that the scrolls were collected from all over ancient Israel and hidden in the cave for safekeeping. Now, the scrolls were written on parchment that was made from animal hide, from sheepskin. Now, if a community living nearby had written all the scrolls, you would expect that the DNA of the sheepskin to be similar to each other, right? That is, it would have been from one flock, or flocks that were descended from each other. Now, if they were collected from all over, the DNA would be different on the scrolls, right? You would be able to tell the difference. Now, what they did is they tested the scrolls and found that the DNA did, in fact, show similarities, and it was from one flock of sheep, meaning that the Dead Sea Scrolls were most likely written by a community that was living in the area. Okay, so we've looked at trace element analysis. You're looking at elements. You can use this to identify the source of something like obsidian. Petrography, you're using polarized light to look at different minerals. It's used for sourcing of clay. Mass spectrometry can help you identify what an unknown substance is, what compound it is. This is good for residues. Carbon-nitrogen isotope analysis done on bones will allow you to understand ancient diet. And genetic analysis will allow you to look at similarities between individuals, animals, and humans, and also ancient populations. In the next video, we're going to begin to look at bioarchaeology, forensic anthropology, and osteoarchaeology. And we'll talk all about all of those, and they all relate to the study of the human skeleton.